Hello and welcome. We're looking today at section 3 on operations as a makeup for me being at a conference in Denver. So let me just go through some of the definitions and examples. We should have talked a little about some mappings on Monday, and let's try to see how that idea can be used to define operations, generic operations, which have specific examples that you've seen already. First, an operation is defined by some symbol. Often we'll use this star or asterisk. I find the star is easier to write quickly. Asterisk takes forever, but the book often will use an asterisk. That's fine. Some symbol on a set. This set could be just a few elements. It could be an infinite number of elements. Just some collection. This operation is a mapping, so it takes one thing or input and pass it on to an output. The mapping is defined by the cross of S and S. This is a way of saying that we have an ordered pair. We have a pair of input values and a single output value. And it's defined by the rule where star of A, let me do this again. Star of A and B is equivalent to A star B, and that equals C. So that is our definition of an operation. It's simply a symbol we use between elements to define what we're doing. Now the symbol can be multiplication, which it often is, but sometimes it's addition or something else. So let's see some examples of what these operations could be, and then we'll analyze their properties. Let's look at an example where S is a set of positive integers. I use a Z plus with a little extra line there. And let's define M star M as M raised to the nth power. So let's think about this for a second. Again, M and N are both in this set of positive integers. If we take M raised to the nth power, are we still in the set of positive integers? Yeah, definitely. The issues we'd have to watch out for is this thing defined? We're dealing with positive integers, so we don't have to work too much about fractional roots, and M is positive, even if it was. Okay, so we have positive powers, integer powers, and positive integer denominators. And we can say that here, exponentiation defines multiplication in the positive integers. So that's one example of this multiplication element that's a little bit different. We're able to restrict our set, and within that restriction, we can generalize outward. What's another example? How about a set of matrices, 2 by 2 matrices here. We'll assume they have real entries. With the product just defined ordinarily by A, B. So let's see. If we take two 2 by 2 matrices and multiply them together, do they create a 2 by 2 matrix? Yeah. So we know that it's going between the pair S and S to S itself. One thing to be careful of is if we tried taking the determinant of a product of 2 matrices, that determinant would reduce the matrices down to a number, and it would not be an operation as we defined it so far. Operations require that we take inputs of one set and get back to inputs of that same set. So we can't reduce matrices down to numbers quite yet. We can look at determinants and how they relate to these operations, but that's a little bit different. So matrix multiplication is an operation as defined because it stays within the structures, the input and output pieces are the same or within the same set. And how do we express this? Well, matrix multiplication can be thought of as composition. Matrix mappings is now, we restricted to 2 by 2 just so it's a little bit easier to come up with examples, but this is generalized to n by n. Let me just show you quickly what. A times B is defined as we have A, 1, 1, A, 1, 2, A, 2, 1, A, 2, 2, multiplying by B, 1, 1, B, 1, 2, B, 2, 1, B, 2, 2. And we get the product. And I'll write these products in terms of summations because that's how we define our dot products. The first summation is a summation of A1K BK1. It's the dot product of the first column of B with the first row of A. You could think of that as column 1 of B, or row 1 of A dotted with column 1 of B. Moving down, we dot our first column with the second row, so we get A2K, BK1. Those are our 2 dot products. And let me extend it over to dotting with the second column of B That gives us a summation of A1k, bk2, and the summation of A2k, bk2. Again, dotting the second column, bk2s, b12, b22, with either the first row or the second row. So, it's a good example to be more familiar with that summation notation for dot products because it allows us to generalize out to n by n if we need to. But 2 by 2s are a good place to start. Okay, so very different examples here. Let's see if we can throw another one out that's a little bit different. Well, let me restrict this set just a little bit further. Go back 1, 2, and 3. Let's say we have this set of all A matrices that are 2 by 2, and such that the determinant of A is not 0. With operation, with the same operation. So, what is that getting us? Well, it's restricting the pool that this operator is pulling from. And part of that restriction is to see if we have certain properties of these operations. One of these properties we want to think of when I see determinant not equal to 0 is I think, these are invertible matrices. Does the operation have an inverse? Well, now it does. Define. I know the determinant of A not being a 0 is equivalent to A being invertible. Whereas up here, I have a set that does not every matrix, not every element has an inverse. So this is a bit more restrictive of a set, and it allows us to have more better properties to work with. And let me just throw one more restriction in. Let's call this example 4. Let's say instead of having just matrices who determine as non-zero, let's say all matrices U 2 by 2 over the reals. Assume it's over the reals again. Such that U transpose U equals U transpose equals I. With U star V equaling U times V again. Now, the reason I'm using U here is it's referring to the set of unitary matrices, but in this case, it's the real orthogonal. I'll put that over the reals just so keep that straight. Real orthogonal just means we have real matrices whose transpose is their inverse. That's what this is saying. Whose transpose is its own inverse. Okay, so those are our 3 examples we're going to work with, and we're going to look at 4 different properties of operations that are important to developing groups. So I'm going to erase this and then go through those specific. I'm going to go through these properties one by one, and then specifically look at each of these examples and how they apply to it. So we're using the same definition of the operation. Operation is going between S cross S, so ordered pair, 2S, so all of these ordered elements are defined there. And the term we're looking at is associative. I'm going to erase the commentary. We know how to work with multiplication. Okay, so is exponentiation associative? Well, let's try out an example here. What it means for exponentiation is that we have a tower of exponentials. And the question is, can we reorganize that tower in different ways? Now, I remember from calculus, this is one of those classic examples where reordering tower functions can cause some problems. So I'm going to try an example. Consider 2 times, let's say, what do we know? We're going to power up 2 to the 3 to the 2, which is 2 like that. And then consider 2 to the 3rd, then raised to 2 powers. So that would be 2 to the 3rd squared. Are those two the same? Think about it. So let me reduce them a little bit just to check, just to verify here. We have 2 and 3 squared is 9, so we have 2 to the 9th. And on the bottom, we have 8. We can think of that as 8 squared, 64. To think about this a little bit more carefully, we can think that if we have 2 to the 3rd and then we raise to the 2nd, we are then multiplying. So it's really quite easy to see this is 2 to the 6th. So this first example, S1, is not associative. It's a nice set, but you're not able to reorder the pairings. What about matrix multiplication? Consider that, which is A BC, and A star B star C, which is A B C. Now, if we went through the 2x2 component definitions for multiplication, this would be a lot of work. But correct. Majored multiplication is associative because it sets up an ordering of compositions. We can think of this as F or A is a function of B is a function of C, which is a function of whatever input we're passing into it. And it doesn't matter whether we combine the two outer functions first and then feed them the output of C, or whether we combine the outer two functions, feed in the input, and then apply A. So thinking of it as function compositions, it's fairly clear to see that these two things are equal. S2 star is associative since matrix multiplication is a composition of functions. Okay, now, does it change when we move to S3 and S4 with that same operation? No. The restriction on the set does not change whether or not the operation is associative. It's the operation itself, the rule itself that determines whether it's associative or not the set. Okay. Same for S3 and the operation, and S4 with the operation star. So notice that I've been using this notation. That's kind of hard to see a little bit there. Let me back up a little bit. S1 comma star. What I'm doing is I'm grouping together the set with an operation. I use that word specifically because that's how we define groups. We'll get to the idea. The idea is to group a set with an operation. Now, not all of these are groups quite yet, but that's what we're trying to do. Is we're trying to group together sets with operations, and so we write them together. Okay, so that's associative. Fairly straightforward, but as you can see, sometimes it falls apart. So good to keep your eye on. Next up, we're going to look at the identity element. I kind of saw that one coming right there, but it's good to go through the steps just to review how that identity element applies to the operation more abstractly. An element E in the set S is an identity element, or just an identity. Ignore that part. If A times E equals E times A equals A for all A and S. This is checking to see if the set includes the identity element for this operation. And does an identity element exist for the operation itself? So let's explore exponentiation. C plus is getting erased a little bit. Now, we usually think of of the identity element as being 1, or possibly 0. But in multiplication, we think of it in terms of the 1. How can we get back to 1? So I want to think about that here. If I have m raised to the n, am I ever going to get back to 1? No. I'm not raising to the 0th power. So my set does not allow me to have a 0, which means, for n, which means that I'm only going to get a 1 if m is 1 and n is anything. So if n is, well, yeah. So I can get 1 if we have 1 here and anything up there, or 1 and 1 right there. But does that work? That's an interesting feature. If I have 1 times n for any positive integer n, that's 1 to the n equals 1. So I can think of that as e times a. There's my a. But if I take n times 1, defined as n to the 1, that gives me n. So I kind of have a half identity element, which is not enough. It does not have an identity. Now this is pretty bad. So we'll look at some other ways of modifying this idea later, but it's a good example to see. So here's an example where it kind of feels like there is identity, but it doesn't work both ways. It's not associative. We saw that the operation itself is not associative, so this makes sense. And an identity element for a set, for an operation, needs to be associative. Okay. Now, as to matrix multiplication, well, is there identity element? Yes. If we take A star I and I star A, we get back to the matrix A itself, so yes. S2 with star has identity element D equal to I. Now, is that different for S3 and S4? Does S3 also, it's restricted, does S3 also include I as a matrix? Well, determinant of I is not 0, so yes. 3 star. How about S4? Does I transpose times itself equal I? Yes, I transposes itself. And then does I find, yep, there we go. S4, comma, star. Okay, so looking so far. Example 1 kind of fell through early. Examples 2 through 4 are doing pretty well. They all are associated. They all have an identity element. What else can we ask for? Well, does every matrix have an inverse? given a set with operation, given set and operation with identity E, then element B in S is the inverse of A in S if A star B equals B star A equals B. And we want to ask is, does every B in S, A in S have an inverse? Okay, let's erase correctly last time. Does not, I would just say, not applicable because there is no inverse to S1 with its operation. We won't even worry about that one. There are some subsequent cases that we have to restrict for later. Let's see. A set of all 2x2 matrices. There's an inverse in there, but there's an identity in there, and some matrices have an inverse, but not all of them. Specifically, the zero matrix has no inverse. There's no inverse B such that A times B equals I. So this set with operation does not have an inverse for every element. What about S3? S3 with matrix multiplication. Well, the problem with this example in S2 was that the zero matrix is not invertible, i.e., its determinant is equal to 0. So if you have the set of all matrices that have a determinant non-zero, then yes, has an inverse for every element. And then what about S4? S4 is a set of unitary or real orthogonal in this case. Well, it's a set of all matrices whose transpose is their own inverse. So the matrices are all invertible. So yes, S4 with star has an inverse for every element. Okay, as you can see, we're moving down the line, right? Each of these examples are failing at different levels so far. So now we're down to S3 and S4. Is there anything to distinguish these two sets with operations? Kind of rhetorical, yes. That thing is commutivity, which is a very important and somewhat elusive property of groups. So our last property related to the operation is whether or not that operation commutes. Not only Can you group things in different orders? Can you actually apply the operation in the reverse order? And I think I might have misspoken a little bit ago. When we have the identity element, we have A times E equals E times A equals A. That shows that the two elements, E and A, commute. And when you have an inverse, A times B equals B times A equals E, that also means that B and A and its inverse, commute. So it's a slightly different. So associativity is when you have more than two operations and you group pairs differently but keep the same order. Commutativity is where you can reorder pairings. An operation star on S, set S, is commutative if A star B equals B star A, get that star in there, for all A and B and S. Okay. Now this has nothing to do with inverses or any elements, so S1 is back at them. Possibly. Let's check 2 star 3 and 3 star 2. Nope. Okay. So close, right? It's been in the doghouse for so long. Poor exponentiation. Not. Okay, what about matrix multiplication? Well, this is one of those warnings we see in differential equations. A times B is not necessarily the same as B times A. So let's find an example so we can break it. So let's try something fairly simple. Let's try something like 1, 1, 0, 0, and 1, 1, 0, 0. They can't be the same matrix because those obviously commute. A times A is A squared. But make them ever so slightly different, and a transpose is a nice tricky way to do that. So A star B, 1, 1, 0, 0, 1, 1, 0, 0. We multiply in, we get 2, 0, 0, 0. And B star A is the reverse order. 1, 1, 1, 1. So no. Nope. S2 star is not commutative. Now, what about S3? S3 restricts things down to having a determinant that's non-zero. So the question is, if the determinant is not zero, are we able to reorder the matrices? That's not really helping us. Well, this last example had matrices that had determinant equal to 0 because they were simple. Let's try modifying it to having matrices that have a non-zero determinant. So let me just add some ones like this. Boop, boop. Okay, so now we have two matrices who have determinant of 1. I'll throw. Oh, where'd it go? Now, put those ones in there. Let's try this out. Okay, so now multiplying my first column through, we get 2 and 1. And then 1 and 1. Okay. Again, multiplying, we get 1, 1. It's already different. And then 1 and 2. It's a little closer. Okay, this is obviously not the same, but I'm kind of excited. I'm a little bit excited about this because they're different in specific ways. This is really exciting. When you have invertible matrices and you change the order of multiplication, some things stay the same. Possibly. And this specifically was determinant equal to 1 matrices, which are very special. We'll see them pop up a little bit. But still, it breaks the commutativity. There may be something going on that's a little bit more interesting we can look at later, but no. It is not commutative. Okay, so here's the setup. What about S4? What does S4 give us that S3 didn't? Well, in our definition, we have that U transpose U equals U times U transpose. So right there, we have a reordering of matrices. Okay, that's interesting. Let's modify our matrices A and B so that they satisfy this U transpose U piece. What would we have to do with A? Well, when we transpose, we end up throwing this one out. So we could do that, make it symmetric. And now U transpose equals itself and identity. That's kind of cheating, I suppose, but that's one example. What can we do with B in a similar way? Well, we could do the same thing. That would be very interesting. But let's say that B is another matrix whose transpose is its own inverse. Let's see. There we go. The transpose is itself, and itself is its own inverse. Kind of interesting. So let's try throwing these together. Just to see what happens. If it does demonstrate it, then that's not necessarily proof of the property, but it gives us an idea. So let's go in there, and then B is 0, 1, 1, 0, 0, 1, and 0, 0. Okay. Now, obviously, A is the identity, so we're going to end up with B in either case. Ta-da! Okay, that wasn't too exciting. This is an interesting collection here. Let's see what we can do with the the objects themselves. We have an example. Sure. Yeah, let me try an example that's not specifically, that's not too general. Let me try a rotation that's not an entity. So we want to look at the rotation by pi over 4. It's not right. Let me see. So there's your cosine is, let's go counterclockwise. So cosine, sine, minus sine. Yeah, we'll rotate counterclockwise. And then for B, there we go. So reflection across the y-axis would keep the y value the same, negate the x value. Okay, so this is a little bit different. These are two different unitary transformations. Real orthogonal transformations, you can see that they're transposed. It's the same, are the inverses. Here, swapping that over there. Yeah, okay. So let's try looking at the two orderings. So I'm going to multiply in. Get a -1, -1, -1, 1. Whereas B star A equals same fraction 2. Take the columns of A and multiply by the rows of B. So -1, 1. Ah, there we go. Broke it. Okay. And for completeness, +1. So we broke it in the off diagonals. Whew. So we had an example that worked, but we're able to dig a little bit deeper, think about some more examples. We didn't have enough information here to prove it. It didn't feel like to me. And so I was trying to dig a little bit further to try different enough examples to make this fail. Now, I will say that if I had chosen two unitary transformations that were the same type, if they were both rotations, for example, I might have had a commutative property. Because if I imagine rotating by angle alpha and then rotating by angle beta, that's the same as rotating by angle beta and then rotating by angle alpha. So that further restricted set would be commutative if you looked at just rotations. And we will. Rotations are a very, very important special subset of groups. We think about this in terms of symmetry, and we'll do a big project right around spring break that's focused on the different kinds of symmetry patterns that can come up with groups. And this is one example. Here we have rotations forming a set that does form a commutative collection for the operation, whereas unitary is not quite there. It's close, but not quite there. Whew, okay, that was a lot, but again, this section is really just like previewing groups. And so we're digging into some examples just to see some weird things that are out there, how they're slightly different, and then we'll kind of pull it together, learn some terminology, and start back at the beginning. Start back at the beginning and steadily work ourselves back up. Hope you have a good day, and I will catch you next week.